So in this video, I'm going to talk to you about two different logic gates, one that you've seen before and one that you haven't seen yet. This is actually going to wrap up our discussion on different logic gates. We aren't going to see any more new logic gates after this video. So the gate that you've already seen before is the XOR gate, or the exclusive OR gate that you see here on the screen. Right? The way that an exclusive OR gate works is very similar to an OR gate, except for this last condition. When both inputs are high, an exclusive OR gate is low. A traditional OR gate would be high here. These exclusive OR gates have some very interesting purposes. The textbook covers some of the purposes, some of the useful features of exclusive OR. We're actually going to see some other useful features of exclusive OR after the first exam. So there will be more information about that coming up very soon. Finally, just to wrap up, once and for all, some confusion about the first homework assignment. Here we see an example of an exclusive OR gate that has multiple inputs. If you remember, this was a question that was on the first homework assignment where I asked you to create one of these and draw a transistor level diagram, transistor level circuit of such an exclusive OR gate. The textbook presents an exclusive OR gate in this fashion, where the truth table, you can see that if there are an odd number of ones coming in, then the output is true. If there are an even number of ones coming in, then the output is false. So a multiple input exclusive OR gate can be seen as sort of a modulus operation of sorts that's detecting even or odd numbers of inputs. There is another configuration of exclusive OR gates that suggests the output should be high if exactly one of the inputs is high. And that's actually what I was recommending people worked on for the first homework assignment. However, I did, of course, accept this if this is the configuration that you used. So I apologize for the confusion. There are, in fact, multiple configurations for this exclusive OR gate. And we will probably see both configurations as we move on throughout the semester. So that's the old gate. That's the gate that you've already seen before. The new gate that I wanted to talk to you about is this one, Xnor. So as its name kind of implies, and you can see from the diagram, it's the inverse of an exclusive OR gate. An exclusive OR gate outputs high if exactly one of the inputs is high. An XNOR gate will output true if both of the inputs are the same, if they're both false or both true. So you can see here the diagram, the truth table, as well as the VHDL for how to create an XNOR gate. These gates aren't very commonly used. We're not going to see them a whole lot, but they will pop up every once in a while, so it's good to know what they are and how they work. I think the most interesting thing about the XNOR gate is how to derive this using Boolean algebra. So up here at the top, you can see I start with an XOR, which is just the inverse of an XOR, rather, which should give me an XNOR if I can find the appropriate steps through Boolean algebra. So exclusive OR can be defined as exactly one input being high. That's A naught and B, or A and B naught. And I still have the inverse here on the outside. So what I'm going to do is apply De Morgan's law, right? That gets rid of this inverse, but requires that I invert both the left and the right-hand side of that OR operation, and then the OR operation becomes an AND operation. And then I'll go ahead and apply De Morgan's law once again to the step that's inside the parentheses. That will get rid of these inversions on the outside of the parentheses, but requires me to invert both of the values inside the parentheses and turn the ANDs into ORs. That leads to this step here. Some of these terms have two inversions on them, which will cancel out, leading to this line. Next, I can distribute using FOIL method to come up with this equation here. You'll notice that the first and the last equations, A and A naught, B naught and B, are proven false. There's no way that these can ever be true because of the nature of AND. So those terms drop out, and what I'm left with is A and B, or A naught and B naught, which is the exact definition of an XNOR gate, as you can see from the truth table on this slide. So in the next video, we're going to start wiring gates together to create useful circuit components that we're going to start putting together for use in our larger, more complicated circuits in the second and third parts of the semester.